Hello, welcome. My name is Rio. I am going to be talking about tracing your distributed systems with the OpenTracing project. I work here at the Ambassadors. Ambassadors is a creative production studio that mostly works on TV commercials. And instead of talking about it, I'm just going to show you this. So this was a show reel mainly to accommodate our design and animation team, but in reality just about any department has touched every commercial that you just saw in some way. We do visual effects, edit, color, music, you name it. And the department I work for is called the Lab. We try to tackle problems in a creative way, but also doing projects not directly related to TV commercials. You have to think about projects like virtual reality experiences or interactive installations. But also a project called Cube, which is a web platform that came out of to be out of a problem that back when the TV stations went from analog to digital, a lot of people didn't know what to do with these very high quality digital video files that were produced by us at the Ambassadors, because usually most computers weren't able to actually play it and that kind of stuff. So Cube actually stores those files on the web, makes them viewable on a web browser, and our customers can use that to do reviews on them, approve them, and eventually send them on to the broadcasting stations themselves. Now we also created a module called Compose, which actually enables us and our customers to on the fly generate these TV commercials based on a template that's usually built by our visual effects team or somebody at the lab. You have to think about commercials that often change their pricing or languages or backdrops that are used. And again, they can send it directly to the TV stations. So this is a video that we made in I think 2014, reintroducing Cube as a version 2 project. And coincidentally, it also illustrates the architectural changes that it went through in the years. We've seen it develop from a single-threaded Python application to a multi-threaded one, all the way up to micro and not so micro services. But the same problem kept creeping up. How can we maintain visibility and observability in a system that keeps expanding and sometimes contracting as well? So one of the things I've been doing in the years is just keeping an eye out for projects and tools that help us maintain that level of visibility and hopefully increase it as well. Everybody knows this. These are called logs for people who don't know it. They're meant to show events happening in certain parts of your system, but they're usually constrained to a small part of your system and not crossing any other boundaries without any additional tooling. Another thing you might be using is metrics. Metrics are small pieces of data that can be aggregated to answer questions like how many requests per second are we currently serving, how many of those are errors, and how long are they taking. But there's this gap that's not directly addressed by any of these two technologies. In this case, request scoped information. This request that just came in, which services did it hit, in what order, and how long did it take? That's where the OpenTracing project comes in. OpenTracing is now served by the CNCF, the Cloud Native Computing Foundation, alongside of projects like Kubernetes, Prometheus, Linkerd. Those projects are all software binaries usually that you can just install and start using. OpenTracing is more of a specification for an API. It does have implementations in different languages, but those libraries don't actually do anything in and of themselves. And I'll come back to that later. So just to start out, what's a trace? A trace is a collection of spans that each span individually will represent a single unit of work that's being done. They have a name usually, a starting time and a finishing time, but also a relationship between each other. So usually it's a parent-child relationship that they have. They can contain other information. We call them tags, simple key-value pairs that describe something about the unit of work that's being done at that time. Logs are also part of a span. They fulfill the same role as a normal log would. They're just like tags, except they're time-stamped. So they're time-stamped to that specific span that they are associated with. Then there's this special kind of tag called baggage, again just like tags, except they travel with the trace. So whenever a trace jumps a service, for example, whatever information is contained in baggage will actually jump with it. It's a very powerful concept that you can use, but it's very dangerous because if you put too much data in there, it might increase your network load exponentially. So just to give you an overview, this might be a request for a resource that just came in on your API gateway. And one of the things that need to happen is to see if the user that requests them is actually authorized to do that. So it will start some process either in the same binary or somewhere else in the system that tries to retrieve information about the user and then make a call if that user is authorized or not. And eventually, if everything goes well, the service responsible for that resource will return whatever data is requested. Now, the thing to note is that the borders between these spans can be just about anything. OpenTracing doesn't care what it is. As long as its tracing context is able to jump over those things, your trace will continue and expand. So these things could be network request calls or simply information that's being passed between program threads. So what would this look like in code? This is the authorization function I was talking about, written in Go. It takes a context as a first argument, user ID as a second, and will return an error if anything goes wrong. This is the function that resolves the user information from the user ID. This is where we check where the user is, if the user is authorized or not, and if he isn't, we return an error. Otherwise, we return nothing. Everything's fine. So if you'd like to trace something like this, the first thing you do is start a span. Now the OpenTracing library in Go has a start span from context function that takes a context, tries to find a span in it, starts a new span with the previous span as its parent, give it a name, in this case just auth, returns the newly created span and the newly created context that contains that span. Contexts within Go is a way to pass around metadata, request scope metadata inside a single binary. It's a language feature which I really enjoy. One of the last things that you need to do is actually finish that span so we have a start and an end time again, because if you don't, the span will not be collected and it won't show up anywhere in your traces. I'm using the defer keyword here that tells Go that whenever the auth function goes out of scope, run that finish command. So I'm assured that it will be run at some point. As for tags, the user ID might be a nice thing to tag on this span. Tags are, as I said, key value pairs where the keys are always strings. These strings are freeform. I'm using the user.id notation here, but you can use just about anything. There are conventions for this. They're all specified in the specification of OpenTracing. Something like http.method will contain the method being used for a span associated with an HTTP request. Something along those lines. If the user is not authorized, might be handy to log it, so we do that. The span.log fields is a logger that can take a number of fields. In this case, it's just a single field, which is a string with the event as a key and unauthorized as a value. So, if you'd like to start using something like OpenTracing, where would you begin? Most likely, you won't be coding anything. If you look at your RPC layer that you're using, or your mesh network like Linkerd or Akka or gRPC, they probably have hooks or implementations already done for you that you can just inject anywhere inside of that layer, and your traces will start to appear in the tracer that you're using. The reason I start with the RPC layer is because they're the input and output of every service probably inside of your system, so you can easily build up a map of your system looking at how every service is talking to each other. Next up would be a web framework. Django, Spring Cloud, all those kinds of frameworks probably have OpenTracing already implemented. Usually these frameworks go pretty deep inside of your stack, so it also covers a large amount of your services. The proxy that you're using, Nginx, has a module that can start traces for you. It will check on an incoming HTTP request if there are traces already present in the headers. It will start a new span regardless and will inject it in the headers for the request bound for whatever backing services that you're using at that moment. Queues in memory data stores like Redis and RabbitMQ also have support for this usually. Usually the databases themselves don't actually know about traces, but it's the drivers that you use in your programs that know about OpenTracing and try to describe any action that you take on that database. Normal databases, ORMs and drivers that you use have the same, probably have the same hooks that you can use for OpenTracing. So as I mentioned, tracers, these libraries don't actually do anything in and of themselves, which makes it safe for you to implement them without actually having a tracer somewhere running. Your program won't crash at all, hopefully, if the library that you use is properly implemented. But you need a tracer either somewhere on your system or somewhere near your binary that can collect all these spans. There are a number of tracers out there. Jaeger is one of them, which is the one we use internally, and it's also the one I'm going to demo now. But there are a number of closed source ones as well, each with their own feature sets that you might or might not like. Incidentally, this is also, in my opinion, the most powerful feature of OpenTracing. It's completely vendor agnostic. So if you find a tracer or want to build a tracer with a specific feature set, you can just plug in a different one, and you don't need to change any code that you already have put it inside of your code for tracing, as long as the tracer that you build or you use will actually adhere to the OpenTracing standard. So Jaeger, demo time. I've got a number of demos here. Let's start with Hot Rod. If there are any questions, by the way, feel free to interrupt. I'm going to just go through these, and if you guys have questions, I'm glad to hear them. Apparently not. I'm doing an awesome job. Yeah. So Hot Rod is an application that is packaged with Jaeger. Jaeger is built by Uber and released as open source last year. And it's, surprise, surprise, a rides-on-demand application. And if I click any one of these buttons, a dispatch request is sent to the backend. It will be resolved, and the driver is dispatched to my location, and it will arrive in a certain amount of time. I'm going to mash this button to trigger a bug that's specifically put in here to showcase a certain feature of OpenTracing. So you see the traces, the request resolving, and if you look at the latency, it starts going up with the number of requests that I'm sending. So this is the Jaeger UI. There's a little Jaeger gopher here. And the first thing I'm going to show you is this dependencies tab. Just by having your system traced Jaeger is able to create a map of your entire system. So the more services that are traced and support open tracing, the more dots you get in your graph. And this is already pretty nice to have. You can easily see that the front end and the routes are talking a lot. The driver service in Redis is also a hot path. So this is already useful information. Now let's see if we can find the trace that I just started. Oh, this is, by the way, readable for everybody. So this is one of the dispatch requests that I just fired. It also contains all the services that are involved in this request. It generated 50 spans and 2 of them have errored. We also see the amount of time that it took, and if we look up here at the scatter plot, these are all the requests I fired, and they increase in duration over time. So if I open this up, this is generally what a trace looks like. Each bar here represents a span and its duration, but also the color indicates which service it originated from. And immediately you can see that this span representing the MySQL select statement is taking almost 80% of the time of this request went into the select. So if I open this one up, we can see the name of the span that got generated, but also the tags that, in this case, the MySQL driver put on the span. Here's one of the conventional tags that I was talking about. Span.kind is usually used to describe what kind of operation was done. In this case, it's the client side of an SQL request. If MySQL was able to do traces, it would generate a trace with span.kind is a server. You can put just about anything in there that you want, but depending on the tracer that you use, it might assign a certain behavior to these kinds of tags. It also stored the MySQL select statement that got fired off, and it logged 2 logs, one of which is telling us that it was waiting behind the log behind 5 transactions, and it also shows us which of the requests were inside of the transaction also waiting for that log. This is a nice example of making a certain part of your system intelligent and showing you what exactly is going on. Yes?
You mentioned that the MySQL driver is adding those spans to the trace.
Yes.
How does it know which query belongs to which request?
Usually there are hooks exposed by those drivers. One example is an ORM called SQL Alchemy, and you can add functionality on certain events like before query or after update and those kinds of things. And those are usually associated with a single call to that driver, and in that way you can add request-specific data to that span. I hope that answered it.
Yeah.
So closing this one up, I'm not going to go very deep in this demo because if you look around YouTube, there are actually loads of these. But I'm going to show you just one more thing. If I zoom in a little bit, you see the stair-stepping pattern. This is a very telltale sign that you might be able to optimize somewhere here. This is a call to the Redis server by the Redis driver, and the first thing that happens here is find driver IDs. Now I assume it would return an array of IDs for a driver, and every other call is called getDriver, which I assume means that it used that driver ID to give more information about the driver, but it's doing it in a sequential pattern. So there might be a way for us to optimize this so it can be done in parallel. I highly encourage you to check out the source code of this. This Redis service and MySQL service is being emulated, and they put some flaws in there to showcase this kind of stuff. Also, what you might notice is this exclamation mark here. If we open it up and look at the tags, there's a tag set called error, which is a boolean set to true, and Jaeger uses this as a sign that the whatever unit of work is being done represented by the span has errored out, so we put an exclamation mark in front of it. If we look at the logs, apparently it was a Redis timeout that happened while getting information from this driver IDs. Right, next demo. So machinery. Machinery is a library for Go that helps handle background jobs. It's comparable to Celery and what's the other one? There's a Java one as well. Anyway, any of those things. There's a queue involved where jobs get posted, workers pull from that queue, work gets done, results get put back on the queue. When I found machinery, there wasn't any tracing involved at all. So I took it upon myself as a challenge, but also just to learn the technology. How would you implement tracing in a very asynchronous piece of software, which is a background job processing queue? So I just started a single Redis server and a single machinery worker, and I am going to send a very artificially generated set of tasks just to showcase what can be done. Let's see, machinery sense. So these are the results of those tasks. As you can see, the first one is a simple addition. An add function is called and it returns a value. These aren't the interesting ones. These are. And when we switch to Jaeger and look at the machinery worker service, we should have one trace. It involves just the sender and the machinery worker. And again, this telltale stair-stepping pattern, and that's because the script simply sends them off one by one, which gives you something like this. I am going to ignore the top ones. But this one is interesting. A group within machinery represents a unit of work that can be done in parallel. So as you can see by the actual work being done by the machinery workers, they are actually done in parallel. But because the sender, actually the library knows what kind of work is going to be done, it can add more informative tags onto the span. For example, the group has an ID. It knows that there are three tasks that can be run, and 10 of them can be run in parallel, so you can just keep adding ones until you go over this number. And it also has the task IDs that are being executed. And if you open up these, you'd actually see that those IDs would be the same. Every task also has a reference back to the group job ID for debugging purposes as well. A variation on the group is a court, which is simply a group of jobs, and each of those results will get fed into a callback function that will then do a multiply of all of the results of those ads. That needs to happen after ads finish. A chain is simply a chain of functions running in sequence as well. This is an interesting one. This one got errored out as well. And if we open the tags, we actually see the error is true again. And if we open the logs, one of the features that we built in is that whenever a panic occurs, the machinery library will try to get the stack trace and log it as well inside of the span. So this is already a very powerful feature to have, especially if you combine it with things like Rollbar or Sentry that do error reporting. So if you actually get the ID that's being used for Sentry and put it in here as well, you get a direct link between those systems without them actually knowing about each other. Any questions? Good.
Rio,
Oh, yes.
could you replace your entire logging system with this?
You can. I don't know if it is advisable. There are projects who do that. Actually, one I'm about to show you did that. Let's see. Of course, like logs are the easiest thing to do. I mean, you just do print line whatever, and you get a file. You get an output on standard out. You can write it to a file and do whatever you want. This is still Linux based, so stream processing is something that's built into the operating system. So logs are definitely a good thing to have, but to be able to get more information out of them, you need to have an entire infrastructure around it. For example, the elk stack and all that kind of stuff, and that gets harder and harder. When you use systems like Kubernetes, well, anybody who's dealt with distributed systems knows the pain of log aggregation. So the last one is called CockroachDB. Anybody heard of that? 2, 3, 4. Amazing. Awesome. So CockroachDB is a distributed SQL database. It can literally span the world, and but it still retains a very high availability and consistency. It also supports fully ACID-like transactions, which immediately sparked my interest because stuff like this is awesome. But they also made the choice very early on in the project to use OpenTracing inside of their logging system. So they, every time they log something, there's a span or a trace active somewhere, it also gets logged to the span, and that way they can very easily debug their entire system. So I started playing with this, and I use it as a guide for me to see how Cockroach actually works internally. So I'm going to try to describe that. Either way, the documentation is also I recommend reading through the architecture articles alongside with these traces, just to see which parts correlate with which parts of the documentation. Let's see, demo time. So this is the admin UI. As you can see, we have 5 nodes running. There are a total of 31 ranges inside of a system. A range is a unit of is a collection of data that Cockroach uses to replicate across nodes. It tries to replicate it at least 3 times, otherwise it will report the range as under-replicated. And as you can see, each node here contains a number of replicas that in total will form 3 times this number. So 93? Yeah, very good at math. So what I'm going to do is, if that didn't already happen here, yes it did. I inserted some, they have a set of example data, in this case a Star Trek database that has 2 tables, which I can actually show you here. It has 2 tables called episodes and quotes, each containing 200 rows. And I forcefully split these tables, which are very small, so they're too small for Cockroach to actually start replicating them in a really meaningful fashion for this demo. I forcefully split all those tables into 5 ranges, and as you can see, this range, for example, got replicated to node 1, 2, 4, and 5, with node 4 having a lease over that range. A lease means that node is responsible for any SQL transaction that happens that involves that one. And you'll see that back in the traces that I'm about to do. So I am going to execute a select statement, joining the episodes and quotes table and looking for Spock. Let's see, I cannot remember my own these. Yes, that's a Docker Compose file. All right, yeah. This will return 55 rows containing 2 columns. The first one is the title of the episode, the characters that were involved, and the last one is the actual quote that was said. And if we go to the Jaeger interface, we press search, select the Cockroach service, press find. I actually need to tell it to filter out everything except SQL transactions. Here we see the select statement that happened. There are 40 spans here. Depending on the way Cockroach replicated the data, it can be anything from 20 spans to 100 spans, also depending on the amount of data that's in your system. This is already a very different trace form-wise than you've seen until now. I'm going to collapse these and open up this one. This is the root trace. The way Cockroach works, every node can be given a query, and that node gets the responsibility of answering that query. It also gets the responsibility of, if we open this log here, of creating a distributed SQL plan. So here we see the select statement come in. It collects the episodes, it collects the tables, that it knows are going to be involved in this select statement. Builds up a distributed SQL plan, which is simply like, I know these nodes are involved, you can do this part of the calculation, you can do this part of the calculation. Which means that whenever your Cockroach cluster grows, your computing power will also go up often. And eventually it will run the SQL plans. If we close this one again, we see this funny thing happening. As I said, Cockroach will use some tags to give special meaning. So here, the gRPC component that Cockroach uses to communicate between nodes tagged this span as a client-side span. And if we close this one up again and open the rest and open the next one, we can see that the server side has received the span. So this trace jumped across the network at least once. Well, actually at least twice. This is the part where a flow starts, and this is where I sometimes get confused. There is a point inside of a transaction where data gets read from disk, and I think it's always inside of this internal batch command. If we open it up, we see logs like from table 51, range 40 to 80, I'm going to wait for a read log and return some data. Usually this goes well, but sometimes, and I hope I can find one, sometimes, nope, it didn't happen. Sometimes the node that's responsible for building the SQL query will actually not know which range is stored where, or it has an assumption that it has. In which case, the node that's executing the query will not find the data it's looking for, and will just try to find the actual node. So there will be an X number amount of other hops that happen inside of the system. So in this case, Cockroach is an awesome thing to look at, and to look at the code just to see how they use OpenTracing, and how I use it as a learning tool as well, to just see how a complex system like Cockroach, which is very easy to operate but very difficult to understand the internals of, just this tool really helped me to understand something like this, and also helped me run it in production eventually. So yes, that's all I've got for today. I want to thank you. If you want to see more stuff that we made, go to our website, ambassadors.studio. If you like to join us or see what we have in store for you guys, then check out careers. This talk and the demos is all visible on GitHub. The only thing that you need to run these demos is Docker and Docker Compose. So they'll probably be easy to set up. Thank you very much. Enjoy the rest of the evening.
Thank you very much. Any questions?
Yeah, any final questions? Yes.
From your experience, do you collect every trace in a production system, or is it too much data?
Depending on your data flow, you could. We don't do it. We haven't seen the need yet, but there are ways to tell OpenTracing to forcefully collect a trace. So you can flip a switch somewhere in the database or an admin panel, and for example, that user will get traced regardless. You could turn it on, but it will exponentially increase your network traffic, which might not be something you want to do. Maybe on a subsystem somewhere. Yeah. Anything else? Yes.
Do you send, so when you have an application that uses OpenTracing,
Yes.
does it send data directly to whatever tracing server there is, or can it be like an intermediate step?
That really depends on the tracer that you're using. In the case of Jaeger, Jaeger is split up in a number of components. One of them is the agent. By default, the Jaeger library will send all the traces to a local host on a certain port via UDP, and the agent will then forward it to the collector. There are tracers. There's one called Lightstep. It's a closed source hosted tracer that does something different, because for one you don't host them, and as a feature they can actually start traces inside of the user's browser, which is a completely different ballgame than a backend system. Cool. Yep.
There was a way to trace only sort of a random amount, right?
Yes, by default, at least the Jaeger tracer does that, and I'm certain a lot of them do. Traces are based on sampling. If you use the production settings, it's like 1 in 1,000 traces get sampled. You can up that trace, and that's also the way that you would forcefully trace something, is by setting the sampling tag. It's actually a tag that you set on a span to 1, and then the tracer will try its best to collect every span generated by the previous spans. Okay. Awesome. I'll be drinking beer afterwards, so there will probably be some more questions I can answer.
Okay, thank you very much, Rio. Again.